Physics faces a deep and troubling contradiction. Our two most powerful theories of reality, general relativity and quantum mechanics, tell completely different stories about the fate of a black hole. One says it is the simplest object in the cosmos. The other says it must hide the universe's most complex secret. By the end of this exploration, you will understand the revolutionary idea that every black hole's surface holds a perfect cosmic record of everything it has ever consumed. This journey begins with a deceptively simple rule called the no-hair theorem. In the classical world of Einstein's gravity, a black hole is defined by just three numbers: its mass, its electric charge, and its spin. Throw a library, a planet, or a spaceship into one, and all those unique details are seemingly erased, leaving behind an identical dark sphere. So here is the devastating question. What happens to all that information? If it is truly lost forever, it shatters a foundational law of quantum physics, creating the infamous black hole information paradox. Solving this is not just about understanding black holes, it is the key to unlocking the final theory of everything. How can something so massive be described by so little? This elegant simplicity captivated physicists for decades. A black hole born from the chaotic collapse of a star became a perfectly clean slate in the universe. It did not matter if the original star was made of iron or hydrogen, if it had a name or a history. All of that was washed away by the immense gravity, leaving a celestial object so simple it could be described with just three numbers, like a cosmic identification card. This is the essence of the no-hair theorem. The three hairs are mass, electric charge, and spin. Think of it this way. If you were to throw a grand piano into a black hole followed by a truckload of roses, the black hole would not gain a piano hair or a rose hair. It would simply get a little more massive, and its spin might change a tiny bit. The intricate information, the shape of the piano, the scent of the roses, is gone. It is the ultimate act of cosmic forgetting. A more visceral analogy is burning a book. The physical pages turn to ash, which still has mass, but the story written upon them, the information, is irretrievably lost to the flames. For a long time, this was seen as a beautiful feature of Einstein's theory, a final state of maximum entropy where nature's complexity was smoothed into perfect, predictable geometry. The event horizon, the point of no return, was not a physical surface but a mathematical boundary, perfectly smooth and featureless. Yet this very perfection sowed the seeds of a crisis. If a black hole truly has no hair, then what happens to the quantum information of every particle that falls in? But that smooth, featureless horizon hides a storm of quantum activity. In 1974, Stephen Hawking made a startling calculation that changed everything. He realized that the empty space just outside a black hole is not truly empty. According to quantum theory, pairs of particles and their antiparticles constantly flicker into existence and annihilate each other in a vacuum. Normally, this happens too quickly to notice. However, at the very edge of a black hole's immense gravity, something extraordinary can occur. One of these virtual particles might fall across the event horizon while its partner escapes into space. The escaped particle becomes real, carrying away a tiny bit of the black hole's energy. This is Hawking radiation. Over immense stretches of time, this slow leak of energy causes the black hole to shrink and eventually, in theory, evaporate completely. The problem is the nature of this radiation. Hawking showed it is thermal, like the glow from a hot stove. It is random noise, carrying no specific details, no fingerprints of what fell in. This creates a devastating paradox. Imagine our book burning analogy again, but now the ashes themselves eventually vanish into thin air. If a black hole forms from a collapsed star, radiates for eons, and then disappears, what happens to the quantum information that made up that star? According to Hawking's original work, it is erased from the universe forever. This violates a sacred rule of quantum mechanics called unitarity, the principle that information is never truly lost, only scrambled and transformed. The universe, at its most fundamental level, is supposed to keep perfect records. A black hole's complete evaporation seemed to burn those records, leaving physics with an impossible contradiction between the smooth geometry of general relativity and the unbreakable rules of the quantum world. This is where a beautiful mathematical puzzle transforms into a full-scale emergency for our understanding of reality. The stakes of the information paradox are not merely academic, they are foundational. At the heart of quantum mechanics lies a principle so fundamental, it is the bedrock of how we calculate anything in the quantum world: unitarity. Think of it as the universe's ultimate accounting system. In any quantum process, information is never deleted, it is only ever rearranged. If you know the complete quantum state of a system at one moment, the laws of physics guarantee you can, in principle, work backwards to reconstruct its entire past. It is a perfectly reversible ledger. This is why we can run complex simulations of particle collisions and trust the results. The mathematics demands that information be preserved. Now place this against Hawking's bleak picture. A unique star with a specific history collapses, forms a black hole, and that hole radiates away into a formless, random haze of heat. The final state after total evaporation is just thermal radiation, identical no matter what you started with. The ledger has been incinerated. The universe's perfect accounting system has a black hole-shaped hole in it, and money, or rather information, is pouring out. This forces a terrifying either-or scenario. Either our cherished principle of unitarity, the rule that makes quantum mechanics work, is simply wrong when gravity gets extreme, or Hawking's elegant derivation within classical general relativity is missing a crucial piece of the quantum puzzle. One of our two great pillars of physics must crack. That is the true weight of the paradox. It is not just a debate about what happens inside a black hole. It is a direct challenge to the logical consistency of the laws governing our entire cosmos. Solving it is the essential step toward the holy grail of physics, a theory of quantum gravity that seamlessly unites the very large with the very small. The fate of information is the thread that could unravel everything or weave it all together. The first desperate hope for a solution was a beautiful, subtle idea. Perhaps the information is not lost at all, but instead escapes, hidden within the Hawking radiation itself. The radiation might look random and thermal, but what if its specific pattern of particles, the exact timing and energies, contained a fiendishly complex code? A code that perfectly described everything that ever fell into the black hole, scrambled beyond recognition, like a book shredded and its confetti scattered to the wind. In principle, a being with infinite knowledge and computing power could collect every single photon of Hawking radiation over the black hole's entire lifetime, and through unimaginably complex calculations, reconstruct the original star, the piano, the roses. This idea preserved unitarity, the universe's ledger. The information would be outrageously difficult to read, but it would not be erased. For a while, this seemed like the perfect escape hatch from the paradox. The black hole could be simple on the outside, as general relativity demanded, yet the information about its past could still exist, imprinted on the radiation it emitted. But this elegant hope soon ran into a wall of quantum logic. The problem is one of connection. Hawking radiation is created in the empty space just outside the event horizon, a region governed by the gentle rules of quantum field theory. The information, however, is from all the matter that has fallen through that horizon and now resides in the mysterious interior, a realm of crushing gravity. How does the information about the interior get out to be imprinted on the escaping radiation? There is no classical channel, no pathway for a signal to travel from inside the black hole to the outside. The only conceivable link is a purely quantum one, a phenomenon called entanglement. In the Hawking process, the pair of virtual particles are born entangled, their fates intrinsically linked. When one falls in and the other escapes, the escaping particle remains quantumly entangled with its partner now inside the black hole. This creates a delicate web. The Hawking radiation outside is entangled with the interior state of the black hole. This entanglement is the proposed carrier of the information, but this solution creates a new and perhaps more violent paradox. As the black hole evaporates over eons, the Hawking radiation it emitted early on travels far away into space. That early radiation must remain entangled with the interior. However, for the final piece of radiation emitted just before the black hole vanishes to also carry information, it too must become entangled with all the radiation that came before it. Here lies the catastrophic snag. In quantum mechanics, you cannot simply share entanglement. A particle cannot be fully entangled with two different systems at the same time, a rule called monogamy of entanglement. So the late-time radiation faces an impossible choice. To preserve information, it must be entangled with the early radiation. But to be created via the Hawking process, it must start out entangled with its partner inside the black hole. It cannot do both. If the entanglement with the interior is violently broken to allow the new entanglement with the early radiation, it would create an inferno of energy right at the event horizon, a wall of fire that would incinerate anything trying to cross. This is the infamous firewall paradox. It suggests that saving information from being lost might require destroying the very smooth, placid spacetime that defines a black hole in the first place. The universe seemed to be offering a cruel menu of impossible options: lose information and break quantum mechanics, or create a firewall and break general relativity. Neither was acceptable. The solution would require rethinking the most fundamental aspect of a black hole, the nature of its surface. The deadlock demanded a complete reimagining of space itself. What if the key to the paradox was not about what falls into the black hole, but where its information has been all along? This is where physics took a breathtaking leap into the surreal with the holographic principle. Its core idea is as radical as it is elegant. The information describing everything within a volume of space is not spread throughout that volume, but is instead painted like a cosmic fresco onto its outer boundary. A black hole's interior, with its vast three-dimensional volume, is not the primary reality. The true story is written in two dimensions on the event horizon. The name comes from a familiar security feature on a credit card, a hologram. A holographic sticker is a flat, two-dimensional surface, but when you shine light through it, it projects a full, three-dimensional image. The holographic principle suggests our universe might work in a similar but inverted way. We experience a three-dimensional world, but the fundamental data that creates it could be encoded on a distant, two-dimensional surface. For a black hole, this surface is its event horizon. This was not pure speculation, it had a profound mathematical origin. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that a black hole possesses entropy, a measure of disorder or hidden information. The shocking result was that this entropy was not proportional to the black hole's enormous volume, but to the area of its horizon. This was a monumental clue. In everyday life, entropy scales with volume. Think of the number of ways you can arrange books in a library. It grows with the size of the building. For a black hole, the information capacity grows only with the surface area of the sphere. It was as if the library's entire collection was not on shelves filling the space, but was etched into the very paint on the walls. Physicists Gerard T. Hooft and Leonard Susskind took this clue and ran with it, proposing the holographic principle as a fundamental law of quantum gravity. They argued that because information cannot be destroyed, and a black hole's maximum information is set by its surface area, then all the information about what fell in must be represented on that surface. The three-dimensional interior, with all its mystery, becomes a kind of projected illusion, a cosmic shadow play. The real physics, the complete quantum description of everything the black hole contains, happens on the two-dimensional horizon. This transforms the event horizon from a smooth, passive boundary into the most important object in the universe, a buzzing, active membrane storing the universe's deepest secrets. It redefines the very nature of reality, suggesting that what we perceive as depth and volume is an emergent property, a translation of data written on a distant screen. With this radical canvas in place, the stage was finally set for a concrete solution to the information paradox, one that would weave entanglement and holography into a single, breathtaking tapestry. The holographic principle was a stunning vision, but for years it remained a compelling metaphor. Physics needed a precise mathematical engine to turn this beautiful idea into a calculable reality. That engine arrived in 1997, courtesy of physicist Juan Maldacena, and it is known as the anti-de Sitter conformal field theory correspondence, or AD-CFFT for short. While the name sounds intimidating, its core idea is a revelation of cosmic proportions. It proposes a perfect duality, meaning two completely different descriptions of the same physical reality. On one side of this duality, you have a universe that contains gravity and black holes, described by string theory, living in a special type of curved space called anti-de Sitter space. Think of this as a vast cosmic chamber with reflective walls. On the other side, living precisely on the boundary of that chamber, is a quantum theory of particles that has no gravity at all, a conformal field theory. The miracle of the AD-CFFT correspondence is this: every single event, every process, every bit of information that happens in the gravitational interior with its black holes, has a perfect one-to-one translation into the language of particles interacting on the boundary. They are not just similar, they are mathematically identical, two sides of the same coin. This is the holographic principle in its most powerful and precise form. The entire three-dimensional drama of spacetime, matter, and gravity is encoded on a two-dimensional screen. For the black hole information paradox, this is a game-changer. In the boundary theory, the conformal field theory, there is no black hole. There is only a hot, dense plasma of interacting quantum particles. And in this purely quantum system, the rules are clear: information is never lost, unitarity is strictly preserved. The calculations are difficult, but the principle is ironclad. Because the two descriptions are equivalent, what is true on the boundary must be true in the bulk. Therefore, the information that falls into the black hole in the gravitational description cannot be lost. It is merely transformed into the intricate patterns of that hot quantum soup on the boundary. The paradox in this precise mathematical universe is resolved. Information is preserved because it was never truly inside the black hole to begin lost. It was always on the surface, dancing in the quantum degrees of freedom of the boundary theory. The AD-CFFT correspondence provided the first concrete proof of concept that a theory of quantum gravity could be unitary, that it could respect the universe's perfect ledger. It showed that the holographic principle was not just philosophy, but a potentially rigorous framework for physics. Yet this triumphant answer came with a profound caveat: our universe is not an anti-de Sitter space. We live in an expanding cosmos with positive energy, a de Sitter-like space. So the question became, does the lesson of AD-CFFT, the salvation of information, apply to the real black holes in our real sky? Yet the triumph of holography and AD-CFFT presented a new puzzle. If a black hole's information is perfectly encoded on its two-dimensional boundary, then what does that say about the classical, three-dimensional black hole we thought we knew? It forces us to revisit the very idea that started this crisis, the no-hair theorem. That elegant rule from Einstein's era declared a black hole to be bald, defined only by mass, charge, and spin. But in a quantum universe where information is preserved, can it truly be so featureless? The answer emerging from the frontier of physics is a fascinating no. The no-hair theorem is meeting its quantum demise, and in its place is growing the concept of quantum hair. This is not hair in any literal sense, of course. It refers to subtle, persistent imprints left on the very fabric of spacetime surrounding a black hole. According to the classical theorem, if you throw a complex object like a magnet into a black hole, its specific magnetic field pattern should be swallowed and erased, leaving only a possible change in the hole's total electric charge. But quantum effects tell a different story. Recent theoretical work suggests that fields, including electromagnetic fields, can leave behind faint but permanent distortions in the gravitational field itself. These are not the three classical hairs, but a whole spectrum of finer details called multipole moments. Think of it like the difference between describing a sphere and describing a planet. A perfect sphere is defined by its radius alone, but a planet, while roughly spherical, has mountains, valleys, and a slightly bulging equator, all of which can be described by more complex mathematical terms, the multipoles. A classically bald black hole is that perfect sphere. A quantum black hole with hair is more like the planet, possessing a unique gravitational landscape sculpted by what fell into it. How does this work? Imagine our magnet falling toward the event horizon. As it crosses, its specific magnetic field configuration does not simply vanish. Through intricate quantum gravitational interactions, the information about that configuration gets translated into a permanent, subtle tweak to the geometry of spacetime just outside the horizon. It is as if the magnet's signature is not painted on a surface, but woven into the very grain of space. This imprint, this quantum hair, is detectable in principle from a distance by studying how the black hole's gravity influences objects orbiting it or light bending around it. It is a faint whisper of the black hole's history etched into the gravitational field. This discovery begins to profoundly blur the line we have been wrestling with. It suggests that the black hole's surface, its event horizon, is not a passive information screen separate from the interior, but is dynamically linked to it through these quantum gravitational imprints. The information is not just stored, it actively shapes the black hole's external appearance in ways Einstein's pure theory did not predict. The horizon and the information it retains become two aspects of a single, richer quantum entity. This is a quiet revolution, one that is slowly dressing the black hole in the intricate details of its past, proving that even the darkest objects in the cosmos cannot hide their stories completely. Even the most brilliant minds can return to their greatest puzzles. In the final years of his life, Stephen Hawking himself, who had ignited the information paradox with his radiation, turned his focus toward a potential solution. He, along with colleagues Malcolm Perry and Andrew Strominger, proposed a specific and elegant form of quantum hair, something they called soft hair. This idea reaches into one of the most ethereal corners of physics, involving particles that carry no energy at all. These are soft photons and soft gravitons, the gentlest possible ripples in the electromagnetic and gravitational fields. You cannot power a light bulb with a soft photon, nor move a scale with a soft graviton, for they possess zero energy. Yet, in the subtle quantum world, zero does not mean nothing. These zero-energy particles are everywhere, a kind of cosmic background static woven into the fabric of space itself. Hawking and his collaborators realized that when an object falls into a black hole, it can shed an infinite number of these soft particles, like a stone dropping into a pond and creating an intricate pattern of vanishingly faint, frozen ripples on the surface. Each of these soft particles is associated with a conserved quantity, a charge that gets imprinted onto the black hole's event horizon. This imprint is not a physical dent, but something more abstract, a supertranslation. Imagine the horizon not as a rigid sphere, but as a flexible, stretchable fabric. A supertranslation is a specific, subtle rearrangement of every point on that fabric, a gentle stretching and compressing that leaves the overall shape looking like a sphere, but with a unique, hidden fingerprint. Every object that crosses the horizon performs its own unique supertranslation, tweaking the horizon's geometry in a distinct way. The proposal was breathtaking. An infinite number of these soft hair charges, corresponding to an infinite number of possible supertranslations, could reside on the horizon. Together, they might form a vast and nearly limitless code, a cosmic ledger capable of recording the quantum details of everything that ever fell in. The piano, the roses, the library, each would leave its own signature pattern of supertranslations, its own set of soft hairs. This was Hawking's final, profound shift on the paradox he created. He moved from the idea of information being lost to thermal radiation, to the possibility that it is meticulously preserved in the most delicate features of spacetime itself, in the silent symphony of zero-energy particles and the frozen geometry of the horizon. It suggested that the answer to the universe's greatest accounting problem might be written in the faintest possible ink on the surface of the darkest possible objects. Yet this delicate imprint of soft hair points to an even more dynamic reality. The event horizon is not a static ledger, but a seething, chaotic processor. To understand what truly happens to information, we must stop picturing a smooth sphere and start imagining the most powerful and chaotic quantum computer in the universe. When a bit of information, say the quantum state of a single particle, reaches the event horizon, it does not simply land gently on a surface to be recorded. It is violently assimilated. The horizon is theorized to be the fastest scrambler of information in nature. Scrambling is a precise quantum concept. Think of taking a drop of black ink and releasing it into a glass of clear water. At first, you see a dark, coherent swirl, but very quickly, through the chaotic motion of the water molecules, that ink diffuses until every single molecule in the glass holds a nearly imperceptible trace of it. The information of where the ink drop started is not gone. It is just spread so evenly and so thoroughly that you could never reconstruct it by looking at any one part of the water. You would need to analyze the entire glass at once. This is what the horizon does, but at speeds governed by gravity. The fast-scrambling conjecture proposes that a black hole distributes any new information across all of its microscopic quantum degrees of freedom in a time scale proportional to its mass multiplied by the logarithm of its information content. For a stellar mass black hole, this could be mere microseconds. The information is not lost, it is encrypted with a key of unimaginable complexity. From the outside, this process makes the horizon appear thermal and featureless, just as Hawking calculated. The specific details of the ink drop are hidden in the uniform tint of the water. This leads to a profound and beautiful idea: quantum complexity. After the initial, rapid scrambling is complete, the information's journey is not over. The system continues to evolve, weaving the information into more and more intricate patterns of quantum entanglement across the horizon's constituents. This growth of complexity is thought to be what actually builds the interior volume of the black hole. In the holographic view, the three-dimensional space inside the black hole is not a pre-existing stage. It is an emergent illusion, a geometric interpretation of the mind-bogglingly complex quantum state living on the two-dimensional horizon. The horizon is the processor, and the interior is the virtual reality it renders. So when we ask what happened to the book or the piano that fell in, the answer is this: their information was instantly scrambled and encrypted across the horizon's quantum bits. That encrypted data then fueled a computation of ever-increasing complexity, and out of that computation, the experience of falling through a three-dimensional space, the very interior of the black hole, emerges. The volume is not a place you travel to, it is a story the surface tells. This leads us to a connection so profound it feels like science fiction. What if the quantum entanglement linking a particle inside a black hole with its Hawking radiation partner outside is not just a mathematical link but a physical one? This is the heart of the audacious ER equals EPR conjecture. The letters represent two of the greatest ideas in physics. EPR stands for Einstein, Podolsky, and Rosen, who in a famous paper highlighted the strange, spooky connections of quantum entanglement. ER stands for Einstein and Rosen, who later described a theoretical tunnel through spacetime called an Einstein-Rosen bridge, what we popularly call a wormhole. For decades, these were seen as completely separate concepts, one from quantum mechanics, the other from general relativity. The ER equals EPR proposal boldly claims they are two sides of the same coin. It suggests that when two particles become quantumly entangled, they are not just mysteriously linked across space, they are subtly connected by a microscopic, non-traversable wormhole. This wormhole is not a tunnel you could fly a ship through. It is a fragile, quantum gravitational thread woven into the fabric of spacetime itself. Now, apply this to our black hole paradox. Remember the problem: the Hawking particle outside is entangled with its partner inside the black hole. According to this new view, that entanglement is not an abstract entry in a quantum ledger. It is a literal geometric bridge, a tiny ER wormhole connecting the two particles across the vast divide of the event horizon. This changes everything. The information about the interior does not need to send a signal through empty space to reach the outside radiation, a move that would violate causality. Instead, the information is already on the outside because the outside and the inside are connected by this hidden architecture. The wormhole provides a direct, albeit subtle, geometric link. Think of it like a shared secret written on two separate pieces of paper. The entanglement is the secret knowledge. The ER wormhole is the physical act of tearing a single original paper in two, so that the edges of the two pieces fit perfectly together. The information is complete only when you bring the edges back into contact. In this picture, the fiery wall of the firewall paradox simply does not form. There is no need for a violent breaking of entanglement at the horizon, because the entanglement is maintained and embodied by the wormhole itself. The smooth spacetime described by Einstein is preserved, not because information is lost, but because it travels a different path, a shortcut through the quantum geometry of the universe. The interior of the black hole and the distant cloud of Hawking radiation are not separate realms. They are two ends of an immensely complex quantum gravitational tapestry, stitched together by countless microscopic threads. But how do we know this intricate recovery process is truly happening? The answer lies in a deceptively simple graph known as the Page curve. For decades, the battle over the information paradox was fought with equations and thought experiments, but physicist Don Page provided a powerful visual way to track the fate of information. He asked a simple question: if information is preserved, how should the total entropy of the Hawking radiation change over the entire lifetime of a black hole? Entropy, in this context, is a measure of missing information, of disorder. Hawking's original calculation produced a devastatingly simple curve. It started at zero when the black hole first formed, then rose steadily as the thermal, random radiation carried away energy but no information. The curve would peak sharply at the very moment the black hole vanished, representing maximum disorder and permanent information loss. It was a graph of cosmic amnesia. Page's revolutionary insight was to plot what the curve must look like if quantum mechanics is correct and information is ultimately recovered. His curve tells a story of redemption. It begins identically to Hawking's, rising as the early radiation is random and entangled with the black hole interior. But then, at a critical midpoint now called the Page time, something beautiful happens. The curve reaches a peak and begins to fall. This descent is the signal of information purification. After the black hole has evaporated roughly halfway, the radiation it emits is no longer just random heat. It starts to carry away the scrambled information from the interior, disentangling itself from the black hole. As more and more of this purified radiation escapes, the total missing information in the universe decreases. By the time the black hole has completely evaporated, the curve returns to zero. All the information has been radiated back out, scrambled but intact, and the entropy of the radiation system drops back down, signifying that the universe's ledger is balanced. The page curve is the predicted heartbeat of a unitary black hole, a signature that the cosmos remembers. For years, it was a hopeful diagram based on abstract quantum principles, a what-if graph. The monumental breakthrough came when physicists found a way to derive this exact curve not from abstract quantum theory alone, but from the geometry of spacetime itself using the gravitational path integral. This tool, which sums over all possible histories of spacetime, allowed them to calculate the entropy of the radiation by considering specific geometric shapes, like Euclidean wormholes, that connect different parts of the black hole's evolution. The fact that this gravitational calculation produced the page curve was a thunderous confirmation. It demonstrated that the laws of quantum gravity, written in the language of geometry, inherently enforce unitarity. The smooth fall of the page curve from its peak is no longer just a quantum hope, it is a geometric destiny, etched into the very fabric of how spacetime can be woven together. This means the information is not merely saved in some abstract sense, it is systematically and inevitably returned to the universe, completing a cycle of cosmic memory that even a black hole cannot break. The page curve is a prediction, but how does nature actually make it happen? The answer was found not in particles or fields, but in the very shape of spacetime, through a ghostly geometry called the replica wormhole. To understand this, we need to look at the tool physicists use to calculate probabilities in quantum gravity, the gravitational path integral. Think of this as asking the universe for every single possible way a process could unfold, every conceivable shape spacetime could take to get from a starting point to an ending point. You then add up the contributions from all these possible histories to find the most likely outcome. For decades, when physicists calculated the entropy of Hawking radiation using this method, they only considered the simplest, most disconnected spacetime shapes. These shapes gave them Hawking's rising curve, the graph of information loss. They were missing a crucial set of histories. The breakthrough came when researchers realized they had to include geometries where spacetime itself becomes intricately connected in ways that seem to defy classical intuition. These are the replica wormholes. The name comes from the mathematical technique involved, where you make many copies or replicas of the black hole system. A replica wormhole is a single, smooth spacetime geometry that connects these different copies together. Imagine you have two identical books detailing a black hole's history. In the old calculation, these books sat on a shelf separately. The replica wormhole is a physical bridge that stitches the two books together into one continuous, larger volume. This bridge is not a tunnel through our familiar universe, it is a shape in a higher dimensional mathematical space that represents the sum over all histories. Its contribution was always mathematically possible, but it was considered too improbable, too exotic to matter. The revelation was that after the page time, the halfway point of the black hole's evaporation, the contribution from these connected geometries does not just become possible, it becomes dominant. They overtake the disconnected histories. This mathematical shift is what forces the entropy curve to turn over and start falling. Why does this connection cause the entropy to drop? Entropy measures ignorance. In the disconnected picture, the radiation from each replica is separate and random, so our ignorance about the total system is high. But when the replicas are connected by a wormhole, it introduces powerful correlations between them. Information hidden in one copy can be accessed through the bridge from another. This correlation reduces the overall disorder, the overall missing information. It is as if you had two separate, scrambled messages. Alone, each is gibberish. But if you discover they are two halves of a single codebook, suddenly you can decipher both. The replica wormhole is the geometric manifestation of that codebook, proving the radiation is not independent noise, but a correlated, information-rich signal. This was the concrete, mathematical nail in the coffin of the information paradox. The universe, in its most fundamental accounting, does not just allow for information preservation, its very geometry demands it. The smooth descent of the page curve is not a quantum hope, it is a gravitational inevitability woven into the possible shapes of reality itself. So if the information is saved by the geometry of wormholes, what exactly is holding the pen? We have arrived at the most critical redefinition in this entire story. What do physicists truly mean when they speak of the surface of a black hole? It is time to retire the classical image forever. The event horizon you have likely pictured, that crisp mathematical boundary of no return from Einstein's equations, is a powerful illusion. It is a line drawn in the smooth fabric of classical spacetime, a prediction of where light would just fail to escape, but in a quantum universe, such a perfectly sharp, knowable location cannot exist. Quantum mechanics blurs everything, including the point of no return. The real action does not happen at that mathematical abstraction. It happens at what is called the stretched horizon. Think of it this way: the classical event horizon is like the precise shoreline on a map. The stretched horizon is the actual turbulent region where ocean meets land, a zone of crashing waves, shifting sand, and constant interaction. This zone, hovering just a fraction of a millimeter above the mathematical horizon, is where the intense gravitational red shift stretches incoming radiation to nearly infinite wavelengths, freezing it in place from an outside perspective. It is here that the temperature is truly immense and the quantum effects are ferocious. This is the processor. This is the holographic screen. This dynamic quantum gravitational layer is not a place you could touch, it is a state of being. It is the physical manifestation of the dual quantum theory from the AD-CFFT correspondence. All those abstract quantum bits, the qubits storing the information of everything that fell in, they are not floating in empty space. They are the fundamental constituents of this stretched horizon. Each bit is a tiny, vibrating piece of spacetime itself. When we say information is stored on the surface, we mean it is encoded in the specific quantum states of this seething, two-dimensional membrane. This is where the scrambling happens in microseconds, where the entanglement is woven, and where the replica wormholes find their physical roots. The stretched horizon computes, and from that computation, something miraculous emerges, the illusion of a three-dimensional interior. The volume of the black hole, the space you imagine falling through, is not a pre-existing stage. It is a generated reality, a cosmic virtual reality rendered by the extreme quantum complexity of the stretched horizon state. The interior is the story and the horizon is the author. This resolves the central tension. The classical event horizon remains smooth and featureless, preserving the peaceful entry predicted by general relativity. No firewall exists there, but just above it, the quantum-stretched horizon is a frenetic, information-dense firewall, not of flame but of data processing. An object crossing would not hit a wall of energy, it would be transformed, its information instantly scanned and scrambled into the horizon's quantum code. Its journey into a three-dimensional interior is not a voyage into a pit, but the gradual activation of that code, a translation from a two-dimensional record into a three-dimensional experience. So the next time you hear about a black hole's surface, do not picture a static shell. Picture the most dynamic object in the cosmos, a blazing, entangled quantum computer whose calculations literally birth the space that lies within it. The horizon is not a boundary of destruction, but a forge of creation where information is not lost, but rewritten into the very geometry of reality. That final picture of a computed interior leaves us with a profound question. What actually lies beyond the stretched horizon? If the three-dimensional space inside is an emergent story, what is the underlying reality? The answer depends on which quantum gravitational path you follow, and each leads to a radically different vision of the heart of darkness. One of the most startling proposals is the firewall. Born from the entanglement crisis, it suggests that saving information requires a literal wall of searing energy right at the event horizon. In this view, the smooth spacetime of Einstein ends abruptly. An astronaut crossing would not experience gentle free fall, but would be instantly incinerated by a Planck temperature inferno. The firewall is not a structure, it is a violent discontinuity, a place where the quantum entanglement linking the interior to the exterior must be broken to preserve unitarity. It is a stark admission that the classical and quantum pictures of a black hole might be fundamentally incompatible at the boundary, protecting the laws of physics with a barrier of pure chaos. While mathematically a possibility, many physicists see the firewall as a paradox in itself, a sign that our understanding is still incomplete rather than a final description of nature. String theory offers a gentler yet stranger alternative called the fuzzball. In this model, the black hole does not have a vacuum interior with a central singularity at all. Instead, the entire region inside the classical event horizon is filled with a gigantic, tangled ball of fundamental strings and brains, the quantum ingredients of string theory. This fuzzball has no sharp boundary. Its threads extend all the way out to where the horizon would be, creating a fuzzy, quantum surface. There is no empty space to fall into, no point of infinite density. When matter falls onto a fuzzball, it simply merges with this complex quantum structure, adding its information to the intricate weave. The interior is not a place, it is a state, a specific configuration of quantum strings. This elegantly solves the information problem because the information is never trapped behind a horizon. It is manifestly present in the extended, fuzzy quantum object. The classical black hole is a smooth average of an enormous number of possible fuzzball states. Much like a glass of water looks smooth and clear, even though it is a seething mass of molecules. Perhaps the most subtle and compelling answer comes from the mathematics of replica wormholes themselves, leading to the island conjecture. This idea completely redefines the meaning of inside and outside. The calculations show that after the page time, when the black hole is halfway evaporated, a remarkable thing happens. A region inside the event horizon, a disconnected island in the middle of nowhere, becomes quantumly entangled with the distant Hawking radiation that has already escaped. This entanglement is so powerful that, for the purpose of calculating where information resides, this interior island is no longer part of the black hole's private domain. It is, in effect, pulled into the gravitational description of the exterior radiation. The information on that island is not lost deep inside, it is encoded in the radiation cloud far away. Imagine a secret document locked in a vault. The island conjecture reveals that after a certain point, the vault's combination is not inside the vault itself, but is written into the patterns of leaves blowing in a forest 1,000 miles away. The interior becomes an informational hologram projected from the outside. This suggests the true interior of an old black hole is not a separate realm, but a kind of quantum shadow of the radiation, a region whose physical description is inseparable from the data already released. The firewall, the fuzzball, and the island each paint a different portrait of quantum gravity's handiwork. One is a violent boundary, one is a quantum substance, and one is an emergent mirage. They are not necessarily contradictory, but different lenses on the same truth, that the black hole interior is not what we classically imagined. It is a dynamic construct, a story told by the surface, and its final chapter is written not in the silence of a singularity, but in the luminous, information-rich code of Hawking radiation. The most profound ideas in physics must eventually face the cold, hard light of data. For all the elegance of holography and wormholes, the universe does not reveal its secrets through mathematics alone. It demands observation, so we arrive at the ultimate practical question. Can we actually test any of this? Can we find a signature in the cosmos that whispers, yes, information is preserved? The challenge is monumental, bordering on the absurd. We are searching for quantum gravitational effects, which operate at scales a billion times smaller than an atom, on objects that are light years away and shrouded in perfect darkness. Yet, against all odds, the theories are beginning to make concrete, falsifiable predictions, offering faint glimmers of how we might one day know. The first potential signature comes from the most violent events in the universe, the mergers of black holes. When two of these cosmic titans spiral together and collide, they send ripples through spacetime itself, gravitational waves that we can now detect with observatories like LIGO and Virgo. In the classical picture, the final merged black hole rings down like a struck bell, its gravitational wave signal fading smoothly into silence as it settles into a perfect bald sphere. But if the event horizon is a dynamic quantum structure, a stretched horizon or a fuzzball, it might not be perfectly smooth. That quantum fuzz could reflect a tiny portion of the gravitational waves, creating faint echoes in the signal after the main collision. It would be like hearing a distinct, soft reverberation after a gong has seemingly stopped ringing. Searching for these gravitational wave echoes is an active frontier in data analysis. While no conclusive evidence exists yet, the mere possibility transforms these cosmic crashes from just sources of waves into potential probes of the horizon's quantum nature. A second target is the iconic black hole shadow. In 2019, the Event Horizon Telescope gave us the first breathtaking image of the supermassive black hole at the heart of galaxy M87. That dark silhouette, outlined by a ring of glowing gas, is shaped by the extreme bending of light around the event horizon. The precise shape and sharpness of that shadow's edge are dictated by the spacetime geometry right at the horizon. Quantum hair, those subtle imprints from infalling matter, would ever so slightly distort that geometry. Different quantum models, like fuzzballs, predict shadows that are less perfectly circular or have a different level of fuzziness at the boundary compared to the classic predictions of general relativity. As the Event Horizon Telescope and future space-based observatories achieve even higher resolution, they may be able to detect these minute deviations. We would be looking for the ghostly fingerprint of quantum information, etched into the darkness of a shadow 6.5 billion times more massive than our Sun. The most direct test, of course, would be to detect Hawking radiation itself. For a stellar mass black hole, this radiation is trillions of times colder than the cosmic microwave background, utterly drowned out by the noise of the universe. It is hopelessly undetectable with current technology, but physicists are nothing if not creative. There are proposals for creating analog black holes in the lab using supercooled fluids or Bose-Einstein condensates, where sound or light waves can mimic the behavior of particles near an event horizon. In these analog systems, researchers have already detected the analog of Hawking radiation. While these experiments do not test quantum gravity directly, they allow us to study the underlying principles like entanglement and scrambling in a controlled setting. They are wind tunnels for the physics of horizons. Furthermore, some speculative theories suggest that microscopic, primordial black holes created in the early universe might be evaporating explosively today, and their final bursts could, in principle, be detected as unique flashes of gamma rays. Finding such a flash with the right energy signature would be a smoking gun for Hawking radiation, and by extension, the entire information recovery process. The path from theoretical elegance to observational proof is long and shrouded in uncertainty. We are listening for echoes we are not sure exist, scrutinizing shadows for details smaller than our pixels can see, and hunting for radiation too faint to imagine. Yet, this is the scientific process at its most profound. The very fact that these ideas about quantum hair, holographic surfaces, and spacetime wormholes generate specific, testable predictions is a triumph. It means we are not just weaving philosophical tales, we are mapping a territory of reality that, while currently beyond our reach, is undeniably there. Each failed search for an echo or a distortion narrows the possibilities, guiding theorists toward more refined ideas. The universe holds the answer, written in the silent language of gravity and light. Our task is to build instruments sensitive enough and ideas bold enough to finally listen. Entanglement entropy is the silent heartbeat of this entire story. It is the precise mathematical tool that allowed physicists to diagnose the black hole's condition, to measure the flow of information, and ultimately to prove it was saved. To understand its power, we must first see entanglement not as a mere curiosity, but as a physical resource. When two particles are quantumly entangled, their fates are linked in a way that defies classical intuition. Measuring one instantly influences the other, no matter the distance. This connection is not just a link, it is shared existence. Entanglement entropy is the number we use to quantify this sharing, to measure how much information about one system is locked away in its connection to another. For our evaporating black hole, there are two primary systems, the black hole itself, which we can call B, and the cloud of Hawking radiation, R. Initially, when the black hole is young and has just begun to radiate, the escaping particles are entangled with their partners inside. At this stage, the entanglement entropy of the radiation is low because the radiation knows very little on its own. Its story is incomplete without its hidden partners. As more thermal radiation escapes, this entropy grows. The radiation becomes a larger, more disordered system, seemingly independent, and our ignorance about its connection to the black hole interior increases. This is the rising slope of the Page curve, a graph of growing entanglement entropy. But if information is truly preserved, this cannot be the end of the story. The pivotal moment, the Page time, arrives when the black hole has evaporated roughly halfway. Here, the quantum system performs a miraculous feat of accounting. The early radiation, which has been traveling through space for eons, begins to purify. It starts to carry away not just energy, but the scrambled information from the black hole's interior. As this happens, the entanglement between the radiation and the black hole begins to transfer. The late-time radiation becomes entangled with the early radiation, not just with the black hole. This transfer causes the total entanglement entropy of the radiation to stop rising, reach a peak, and then begin to fall. The falling slope of the Page curve is the signature of recovery, the mathematical proof that ignorance is decreasing because information is being revealed. The radiation is no longer a random thermal bath, it is an intricate, correlated message. The ability to derive this precise curve, this specific rise and fall of entanglement entropy from the laws of gravity itself was the final, decisive victory over the paradox. For decades, calculating this in a theory of quantum gravity seemed impossible. The breakthrough came from the holographic principle and those strange replica wormholes. Physicists realized they could compute the entanglement entropy of the radiation by using the gravitational path integral, summing over all possible spacetime geometries that connect different copies or replicas of the black hole system. The astonishing result was that the dominant geometry after the Page time is not a disconnected one, but one where these replicas are stitched together by wormholes. This geometric connection in the gravitational calculation directly produces the falling slope of the Page curve. The mathematics of spacetime geometry itself dictates that entanglement entropy must eventually decrease, forcing the information out. This is why entanglement entropy is the ultimate diagnostic. It is the observable that bridges the two worlds, the quantum description of information and the geometric description of gravity. Its behavior, plotted as the Page curve, is the experimental result we read from the universe's most powerful quantum computer, the black hole. It tells us that entanglement is not just a feature of the system, it is the fundamental currency. Information is stored as entanglement, it is processed by scrambling entanglement, and it is retrieved by transferring entanglement. In the holographic universe, the fabric of spacetime and the web of quantum entanglement may be one and the same, two languages describing a single, profound truth, that nothing, not even the darkness of a black hole, can erase the connections that weave reality together. Yet for all its mathematical elegance, this story of preserved information is not the final word. The debate over what happens inside a black hole remains one of the most contentious in all of physics. While a consensus has indeed shifted toward the idea that information is not lost, formidable critics argue we have merely swapped one paradox for another. The legendary physicist Roger Penrose, for instance, maintains a profound skepticism. He views the unitary evaporation of black holes, the tidy return of all information, as a step too far. Penrose suggests that the loss of information might be a fundamental, necessary feature of quantum gravity, a process where the deterministic rules of quantum mechanics break down in the presence of a singularity. In his view, trying to preserve information at all costs forces us into convoluted contortions like the firewall that may be more unnatural than accepting a slight amendment to quantum law. His stance is a powerful reminder that consensus is not proof, and that the allure of mathematical beauty must always be tempered by physical reality. Another deep criticism strikes at the very heart of the holographic salvation, a problem known as factorization. In the clean mathematical world of the add-CFFT correspondence, the duality works perfectly because the boundary theory is a single, unified quantum system. But for a real black hole formed from a collapsing star in our universe, what exactly is the boundary? Is it the stretched horizon itself? If so, whose perspective defines it? An observer falling in would experience no special surface, while someone watching from afar would see information frozen there. This leads to a troubling question: can a single quantum description truly account for these wildly different experiences? The factorization problem suggests that the quantum description of the interior and the exterior might not be seamlessly connected parts of one theory, but could actually factorize or split into two effectively separate descriptions that cannot be combined into a single causal framework. It hints that a complete theory of quantum gravity might require a radical new kind of physics where a single objective reality, even for a black hole, simply does not exist in the way we classically imagine. This feeds directly into the most vexing open question of all: can the interior spacetime of a black hole be described within a unitary quantum theory at all? We have compelling evidence that information escapes, but do we have a coherent picture of what happens to someone or something that crosses the horizon? The firewall, the fuzzball, and the island conjecture are all attempts to answer this, but each comes with significant baggage. The firewall violates the equivalence principle, a cornerstone of general relativity. The fuzzball, while elegant, lacks a complete dynamical description of how it forms from collapse. The island is a brilliant calculational tool, but it describes the interior in terms of the exterior radiation, leaving the subjective experience of an infalling observer deeply mysterious. We are left with a profound disconnect. The external mathematics of entanglement, entropy, and replica wormholes beautifully shows information is preserved for a distant observer. Yet, we still lack a universally accepted, constructive theory of what that preservation looks and feels like from the inside. It is as if we have perfectly calculated the conservation of mass in a chemical reaction, but have no clear picture of the molecular dance that makes it happen. So where does this leave us? The journey from Hawking's devastating paradox to the page curve is a monumental achievement in theoretical physics. It has shifted the landscape, turning the question from if information is saved to how the universe accomplishes such a feat. The tools of holography and quantum entanglement have provided a powerful, consistent mathematical narrative. Yet the final chapters of this story are still being written, in heated debates at conferences and in dense lines of algebra on blackboards across the world. The true nature of the black hole interior, the reconciliation of the falling observer with the watching universe, and the ultimate formulation of quantum gravity remain the great open frontiers. The black hole, it seems, still guards its deepest secret, not in the silence of its darkness, but in the dazzling, contradictory brilliance of our attempts to understand it. This final picture forces us to confront a staggering possibility about the world we inhabit. If the three-dimensional volume of a black hole is not fundamental, but a holographic projection from a two-dimensional surface, then what about the universe we see every day? The implications ripple outward, suggesting that spacetime itself, the very stage of reality, is not a primary substance but an emergent phenomenon. It is a grand illusion generated by something deeper, a vast, buzzing network of quantum information and entanglement. Our classical perception of a smooth, continuous cosmos with distinct places and distances would be a kind of useful fiction, a coarse-grained approximation that emerges when we zoom out from the frenetic quantum details. Much like a television screen looks like a seamless image from a distance, but up close resolves into countless individual pixels. This redefines one of our most basic intuitions about the world: locality. Locality is the principle that objects are directly influenced only by their immediate surroundings, that signals and forces must travel through the space between points. It is why we do not expect a light switch here to instantly turn on a lamp in another galaxy. Yet, in the holographic view, locality is not a fundamental rule of the deeper reality. On that two-dimensional boundary where the true information lies, there is no inside, no outside, no distance in the way we understand it. All the data is right there, interacting on a single surface. The three-dimensional world with its vast separations emerges from how that information is organized and entangled. The vast gulf between stars, the emptiness of space, is not an empty container. It is a manifestation of a specific pattern of quantum connections on a distant cosmic screen. This turns our understanding inside out. We are not living within a pre-existing spatial arena. We are living within a computation, a story being told by an inconceivably complex quantum system. The solidity of the ground beneath your feet, the vastness of the night sky, the flow of time, all could be secondary qualities, emerging from a substrate that is, at its heart, pure information and relationship. This does not make our reality any less real, but it makes it profoundly relational, a shared experience generated by the universe's deepest level of quantum conversation. It suggests that searching for the fundamental building blocks of reality might not lead us to tiny vibrating strings or indivisible particles, but to bits of information and the threads of entanglement that weave them into the rich spatial tapestry we call home. That paradox, for all its frustration, is a gift. It forces us to invent new physics, to see the universe with fresh eyes. In this sense, black holes are far more than cosmic vacuum cleaners. They are the ultimate laboratories for quantum gravity. Their very nature creates a perfect, if punishing, test bed. Think of any other system in the universe, a star, a galaxy, even the vacuum of space itself. They are messy, filled with complex interactions of countless particles and fields, making it nearly impossible to isolate the pure effects of quantum gravity. But a black hole, thanks to the classical no-hair theorem, is almost absurdly simple. Its external properties are defined by just a handful of numbers. This simplicity provides a pristine, clean slate. When we theorize about what happens at its horizon, we are not wrestling with the chaotic details of stellar composition or galactic magnetic fields. We are confronting the raw interface between quantum mechanics and curved spacetime in its most distilled form. It is the difference between trying to understand the physics of a violin string in the middle of a roaring concert hall versus in a perfectly silent, encoded chamber. The black hole is that silent chamber, amplifying the faintest whispers of quantum gravity so we might finally hear them. The extreme conditions where gravity is so strong that space and time lose their classical meaning are not a bug, they are the entire point of the experiment. We cannot build a particle accelerator powerful enough to reach these energies, but the universe has built these natural accelerators for us, scattered across the cosmos. Every theoretical battle over the fate of information has been a forced innovation. The struggle did not just solve a narrow problem, it forged entirely new tools for understanding reality. Take holography. Before the black hole information paradox forced the issue, the idea that our three-dimensional reality could be a projection from a two-dimensional surface seemed like pure science fiction, a curious mathematical artifact. The desperate need to save information from oblivion pushed this idea from the fringe to the forefront, showing it was not just possible but perhaps necessary. Today, the holographic principle is not confined to black holes. It influences how we think about the entire universe. Some cosmologists seriously explore the possibility that our accelerating cosmos, with its dark energy, might itself be described by a holographic theory on its boundary. The tools developed to calculate entanglement, entropy, and page curves for black holes are now being applied to understand the quantum structure of our own cosmic horizon, the edge of the observable universe. Similarly, the central role of quantum entanglement, once seen as a bizarre quirk, has been elevated to a foundational principle of quantum gravity itself through the ER=EPR conjecture. This realization that the fabric of spacetime might be woven from threads of entanglement is revolutionizing fields far beyond astrophysics. In condensed matter physics, researchers studying strange states of matter, like superconductors or topological insulators, use these same holographic ideas to model complex quantum systems that are otherwise impossible to calculate. They employ a black hole's mathematical description to understand the behavior of electrons in a material, a breathtaking cross-pollination of ideas. The black hole, in its terrifying simplicity, acts as a Rosetta Stone, translating between the language of gravity and the language of quantum matter. It teaches us that the most profound breakthroughs often come from staring into the darkest corners of reality, from being willing to let a single, impossible question dismantle everything we thought we knew. The laboratory walls are the event horizons, and the experiments are conducted not with telescopes and lasers, but with pure thought and the unyielding logic of mathematics. Every solution proposed, from fuzzballs to firewalls to islands, is a detailed experimental prediction from this lab, waiting for the day our instruments catch up to our imagination. While the gravitational path integral offers a geometric solution, another profound vision emerged from a different frontier of physics: string theory. This framework, which seeks to describe all particles and forces as vibrations of tiny strings, provides a tangible, almost architectural picture of what replaces the classical black hole. It is called the fuzzball paradigm, and it proposes that the mysterious event horizon is not just a quantum surface, but a complete geometric transformation. In this view, a black hole is not a region of empty space with a point of infinite density at its center. Instead, the entire interior is filled with a specific, incredibly complex structure, a dense, tangled ball of fundamental strings and the higher dimensional membranes called brain. This object has no sharp horizon, no vacuum interior, and crucially, no singularity. Its threads and folds extend all the way out to where the classical horizon would be, creating a fuzzy, quantum boundary, hence the name fuzzball. Each unique configuration of these strings and brains represents one specific quantum microstate of the black hole. Imagine a library. The classical black hole description, the smooth sphere with a horizon, is like describing the library only by its external dimensions, its mass and its spin. The fuzzball paradigm opens the door and reveals the library's true nature, the individual arrangement of every book on every shelf, Each distinct arrangement of books is a microstate. In the string theory picture, each distinct horizonless fuzzball geometry is a microstate. And just as the library's collection holds all the information contained in its books, the specific structure of each fuzzball microstate explicitly encodes the information of everything that collapsed to form it. When you throw an object into a fuzzball, it does not cross a horizon and disappear into a void. It simply merges with this intricate quantum structure, adding its own unique pattern to the weave, like a new thread being knitted into a vast cosmic tapestry. The information is not hidden behind a barrier, it is manifestly present in the very substance of the object. So where does the classical picture of a smooth, empty black hole come from? It is a powerful illusion, an average. From a great distance or with coarse measurements, the myriad of possible fuzzball microstates all look statistically identical. They have the same mass, the same charge, and the same spin. It is like looking at a glass of water from across the room. It appears smooth, clear, and uniform. But up close, you see it is a seething mass of countless water molecules in constant motion. The smooth water is the average classical description. The individual molecules are the microstates. For a black hole, our telescopes and even our gravitational wave detectors currently see only the smooth classical average, the glass of water. The fuzzball paradigm claims the underlying reality is the frenetic dance of strings. This elegantly solves the information paradox at its root. There is no information loss because there is no horizon to trap information and no singularity to destroy it. The information is always there, stored in the explicit geometry of the fuzzball. An observer falling toward one would not experience a smooth passage through a mathematical boundary. Instead, they would encounter a gradual transition into an extremely dense, complex quantum medium. The journey ends not at a point of infinite curvature, but in a merger with the structure itself. This is a radically concrete vision, one that gives physical form to the holographic principle. The fuzzball's surface is the holographic screen, and its complex interior geometry is the three-dimensional image projected from the data on that screen. It presents the universe not as a container of things, but as a dynamic sculpture of vibrating strings, where even the darkest objects are, upon closer inspection, luminous with intricate quantum detail. String theory paints a vivid picture with vibrating strings, but it is not the only path through the quantum gravitational wilderness. Another profound framework, loop quantum gravity, approaches the cosmic puzzle from a completely different angle. Instead of adding extra dimensions or tiny strings, loop quantum gravity asks a more foundational question. What if spacetime itself is not smooth and continuous, but is woven from indivisible quantum threads? In this view, the fabric of reality is not a canvas, but a network, a tapestry of intersecting loops where each tiny stitch is a quantum of area or volume. This discrete geometry changes everything about how we picture a black hole's core. There is no smooth descent to a singular point of infinite density. Instead, as matter collapses under its own weight, the intense gravity reaches a point where it can no longer squeeze the quantum weave of spacetime any further. The collapse rebounds, the quantum geometry resists, creating a bridge to another region of spacetime, a theoretical tunnel often called a Planck star nestled within the black hole. This is not a wormhole in the classical sense, but a quantum bounce, a transition from a collapsing state to an expanding one, potentially giving rise to a new universe or a white hole on the other side of the event horizon. For the information paradox, this offers a radical escape route. Information that falls into the black hole is not trapped forever on a horizon or scrambled into a fuzzball. It is carried through this quantum gravitational transition, preserved in the rearranged geometry of the rebounding spacetime. The black hole in the loop quantum gravity picture is not a final tomb but a cosmic turnstile. The calculations within this framework are deeply encouraging. By counting the distinct quantum states of geometry on the black hole's horizon, physicists can derive its entropy, and that number matches the famous Bekenstein-Hawking formula. This is a monumental result. It tells us that the information capacity of the horizon arises naturally from the quantized fabric of space, from the myriad ways its fundamental loops can be knotted and connected. Information preservation is not an added feature, it is baked into the discrete architecture of reality. The horizon becomes a specific configuration of quantum geometry, and when the black hole evaporates or transitions, that configuration evolves, carrying the data forward in a new form. This mechanism does not rely on holographic duality or strings. The information is not stored on a two-dimensional screen, but is inherent in the three-dimensional, albeit quantized, structure of the spacetime region itself. It suggests that saving information might not require rewriting the laws of physics, but simply recognizing that spacetime, at its heart, has a granular, atomic structure that prevents the infinite destruction a classical singularity implies. The universe's ledger is balanced because the very paper it is written on, the quantum geometry of space, cannot be torn. The journey through these competing visions reveals a fascinating truth beneath the apparent chaos of ideas. A powerful consensus is quietly taking shape. While physicists may argue passionately over the details, the language they use, and the precise mechanisms involved, the core pillars of this new understanding are becoming remarkably clear. The first and most profound tenet is that information is not lost. After decades of debate, the weight of mathematical evidence from holography, from string theory, and from loop quantum gravity all points in the same direction. The universe's quantum ledger remains balanced even in the face of a black hole. This is no longer a hopeful speculation. It is the demanded outcome of our most advanced calculations. The second pillar tells us where this information resides. It is stored or encoded on or near what we have called the stretched horizon. Whether you describe it as a holographic screen, a buzzing membrane of quantum bits, or the surface of a fuzzball, the location is the same, the boundary layer where gravity becomes quantum. This surface is not a passive wall, it is an active processor, a dynamic system whose microscopic states hold the complete data of the black hole's history. From this flows the third principle. Black hole evaporation is a unitary process. The slow leak of Hawking radiation is not a random thermal death, but a carefully orchestrated decoding. The information, after being scrambled into near invisibility, is gradually purified and radiated back out into the universe, following the precise rise and fall of the page curve. This process is as inevitable and law-governed as the orbit of a planet. Finally, and perhaps most mind-bendingly, the interior of the black hole, the vast three-dimensional space we imagine falling through, is not a fundamental reality. It is an effective description, an emergent illusion generated by the extreme quantum complexity and entanglement of the surface dynamics. The volume is not a place you enter, it is an experience rendered by the computations happening on the boundary. These four ideas form the bedrock of the modern view. The different research programs, with their unique vocabularies, are ultimately describing different facets of this same underlying reality. When a string theorist speaks of a fuzzball, they are giving a concrete shape to the information-rich stretched horizon. When an AD-CFFT researcher talks about replica wormholes stitching together geometries, they are calculating how the surface dynamics enforce unitarity and produce the page curve. When a loop quantum gravity physicist describes quantized threads of space on the horizon, they are explaining the microscopic origin of its information capacity. And when someone proposes quantum hair or soft hair, they are describing how the information on that surface subtly imprints itself on the external gravitational field, leaving a faint but permanent signature. These are not contradictory stories, they are different translations of the same cosmic manuscript. One might use the alphabet of strings, another the grammar of geometry, and a third the syntax of quantum loops, but the narrative they tell is consistent. Information is preserved on a holographic surface, and from that surface, the entire drama of the black hole, both inside and out, is projected into existence. This convergence is a sign of profound progress. It means we are no longer just listing paradoxes. We are constructing a coherent, if bewildering, new picture of quantum spacetime, where the most fundamental ingredients are not things in space, but information and the connections between them. Yet, even with this powerful consensus, the horizon of understanding still holds profound shadows. We have answered the monumental if, but the universe now demands the intricate how. The next frontier of the black hole information paradox is a landscape of exquisite detail, where the grand victory of preservation must be built from microscopic blueprints. One of the deepest remaining mysteries is the precise nature of the horizon's own quantum machinery. We speak of it as a processor, a screen, a stretched horizon buzzing with degrees of freedom. But what, in fundamental physical terms, are those degrees of freedom? Are they tiny loops of quantized space, as loop quantum gravity suggests? Are they the endpoints of strings dangling from a higher dimensional brain, as in some string theory models? Or are they something entirely more abstract, perhaps linked to the quantum era correcting codes that theorists now see as the mathematical structure of holography? We know the horizon must have an enormous capacity to store information, proportional to its area, but we lack the final, specific parts list for the most powerful computer in the cosmos. This is not just an academic exercise. Until we can write down the exact microscopic theory of these horizon constituents and their interactions, we cannot fully derive the process of scrambling and decoding from first principles. We are describing a clock's beautiful, predictable ticking without having fully assembled its gears. This gap leads directly to the most visceral, unresolved question, the experience of the infalling observer. Our external calculations beautifully show information is saved for someone watching from a safe distance. But what about the person crossing the boundary? Can we formulate a single, consistent quantum description that seamlessly includes both perspectives, the one who sees a fiery, information-dense horizon, and the one who feels nothing unusual while falling smoothly through it? This is the heart of the black hole complementarity principle, the idea that both experiences are valid and complementary, like the wave and particle descriptions of light. Yet, making this mathematically precise without running into contradictions like the firewall remains a towering challenge. It asks us to reconcile two seemingly incompatible truths into one coherent theory of quantum gravity, a theory where you are fundamentally changes the story reality tells. The answer may require an even more radical departure from classical intuition, where the very concept of a single, objective sequence of events breaks down. Finally, there is the mechanics of the handoff. We have the page curve, a graph that proves information is recovered. We have the replica wormhole geometry that forces that curve to appear. But can we derive, step by step from the hypothesized microscopic laws of the horizon, exactly how a specific bit of information, say the spin of one particular electron that fell in long ago, makes its way into the precise pattern of a Hawking photon emitted a billion years later? This is the difference between knowing a library's catalog system works and being able to trace the journey of a single returned book from the sorting room back to its exact shelf. The transfer mechanism must be unitary, it must respect causality, and it must be calculable. Current research is diving into the quantum chaos of the horizon, studying how information spreads like a drop of ink in turbulent water, and how the intricate webs of entanglement eventually reconfigure to push that information back out. The focus is shifting from proving preservation exists to reverse engineering the universe's own data retrieval protocol. These are the puzzles that now occupy the leading edges of theoretical physics. They are harder, subtler, and more technical than the original Stark paradox, but they are also signs of immense progress. We are no longer lost in the darkness of contradiction. We are now mapping the intricate circuitry of salvation. Each unanswered question is a guidepost pointing toward the final theory of quantum gravity. The black hole, having taught us that information is indelible, now challenges us to read the fine print written in the geometry of spacetime and the logic of entanglement. The last whispers of the paradox are not cries of confusion, but precise and demanding questions, asking us to complete the revolution it began. From a featureless sphere defined by 3 numbers to a buzzing holographic processor woven from entanglement, our understanding of the black hole has undergone a quiet revolution. The classical no-hair theorem painted a picture of perfect cosmic simplicity, a final state where all details were erased. But the relentless logic of quantum mechanics demanded a richer story, one where information could not be so easily destroyed. That demand led us into the heart of a paradox that seemed to threaten the very foundations of physics, only to guide us toward a far more profound vision of reality. We discovered that the black hole's surface, once thought to be a smooth mathematical boundary, is in truth a dynamic quantum system. It is a stretched horizon, a fuzzball boundary, a holographic screen where the information of everything that ever fell in is not lost but meticulously scrambled and stored. This information is not trapped forever. Through the intricate geometry of replica wormholes and the inevitable logic of the page curve, it is gradually purified and returned to the universe in the Hawking radiation, preserving the quantum ledger. The journey to this answer has forced us to reimagine the fabric of the cosmos itself. Spacetime is no longer the primary stage, but an emergent phenomenon, a story told by the quantum entanglement and information living on lower dimensional surfaces. The black hole interior is not a pre-existing place, but an experience rendered by the extreme computational complexity of its boundary. In solving the information paradox, we have not just saved a few bits of data, we have transformed our view of quantum gravity. Black holes are no longer seen as simple holes in spacetime, but as the most complex objects in the universe, natural laboratories where the deepest laws of physics are written in the language of geometry and information. Their darkness is not an absence, but a density of meaning. If this journey has sparked your curiosity, the exploration is far from over. The quest for a complete theory of quantum gravity continues, with new ideas like the holographic nature of our entire cosmos and the quantum structure of spacetime itself waiting to be discovered. The universe's greatest mysteries often begin by staring into the darkest places and asking the simplest, most impossible questions.